Uh, Let us collect today's start with Professor Wang talk. Professor Xiaolong Wang is an assistant professor in the ECE department at the University of California, San Diego. He is affiliated with the CSE department, Center for Visual Computing and Contextual Robotics Institute, and the TILOS NSF AI Institute. He received his PhD in robotics at Carnegie Mellon University. His postdoctoral training was at the University of California, Berkeley. His research focuses on the intersection between computer vision and robotics. He is particularly interested in learning visual representation from videos in a self-supervised manner and uses this representation to guide robots to learn. Xiaolong is the area chair of CVPR, ICCV, and ECCV. He has co-organized multiple workshops and tutorials in CVPR, ICCV, ECCV, and ICLR. He is the recipient of Facebook Fellowship and Video Fellowship and Sony Research Award. So, Professor, please start.
Okay. Yeah. Thank you for the introduction. Let me share my screen. Okay. Yeah, I can start. Nice to meet to present here. So I'm Xiaolong from UC San Diego. So our lab is mostly focusing on the topic in the intersection between vision and robotics. So for this talk, I will mainly talk about some work in vision and then how this can help some robotics tasks we are doing. So if you have any questions, just please ask in the middle. So I will stop. Also, just we can have more frequent discussions on the topics. Okay. So let's first take a look at this video. So in here, both the baby and the dog observe and act in a very dynamic environment. So to understand that act with our visual world, we will need to understand the geometry of the objects, how the object moves dynamically. Oh, sorry, how the object moves dynamically, and sometimes understand the semantics is also very helpful because we all know the ball is safe to play for both the baby and the dog. So can we use this knowledge of 3D and semantics and dynamics of the world to help robots to act? So in the past few years, there are lots of advances in robot learning. So doing different robotics tasks. However, we all see these kind of experiments kind of in the lab environment. We still have no robots that is able to deal with environment like this. Although this is a little bit very ambitious, I can say, to deal with this kind of environment. But then you can see there is actually a very large contrast between in the lab environment and actually what is happening in the real world. So in our line of research, we basically try to argue that the key to deal with the real world problem for perception is to learn rich and generalizable visual representations. So how to learn a good visual semantics representations? So we do see a lot of success, like using human labels to learn with different like recognition systems. So besides the cost of labeling, it is also very constrained by the number of categories actually. So you can only have a limited categories in doing fully supervised learning when you train a system. So then especially for this kind of segmentation task, there will be not enough data for supervising large scale categories, and it is very hard to deal with unseen categories as well. So makes the generalization very hard. So in the 3D world, labeling 3D is also very hard. For example, to label the 3D hand and object poses will require some special constraint in the lab environment and tracking devices. For example, on the right, we can see some motion captures on the hand when they try to label the 3D hand in here. And then for the very popular LERV in here, we also see that a lot of training of LERV is highly constrained by the provide of camera, or maybe it's very hard to train a lot on diverse environments because it's a lot of times the camera is not provided from in the wild videos. So in these talks, we basically try to propose to learn rich representations for both semantics and 3Ds. And we would like to generalize semantic representation learning beyond fixed number of categories. We also like to generalize 3D representation learning beyond constrained environments, but it should be able to train on diverse videos instead of a constrained and small set of videos or multi-view data. So besides the generalization in perception, a rich understanding of human behavior can also provide guidance for robots to perform imitation learning. So I will talk about several ways to collect this kind of human demonstrations to help this robot manipulation task and achieve more generalizable skill learning. So as a short summary, basically, these are some topics I will talk about today and the work we have been doing in the lab. So we have worked on a lot of vision topics and then use robot learning to apply these vision technologies to a lot of different manipulation tasks and navigation tasks. Okay, so I will start from the vision part. So particularly, I will talk about this work of group VIT that presented in CVPR 2022. So in this work, we basically try to perform like semantic segmentation, but without using any pixel-wise labels. So the work is quite straightforward. It's basically you given an image, you first do some grouping on top of the image, and then you can label the groups with the semantic information. And here is a lot of examples. You can group any images into regions and then label the regions with the semantics labels. So in this whole process, I think the interesting part in here is that we didn't need to use any pixel-wise labels, and then it is not performing in the fixed categories. It is performing in the open vocabulary. So specifically in training time, we basically only required image text pairs, a large scale image text pairs. Initially, we train on 30 million, and then later we train on 400 million size of data sets. So we train our group VIT with these image text pairs. It automatically learns to group the pixels into regions. And then during test time, given any input image, we can first use the group VIT to generate the segments. And then we have another text encoder, which is trained together during training time to basically label the segments with the query words. So the whole training process is only using image and text. You can think it like clip, but it is not just a clip for zero-shot image classification. It is basically clip for kind of clip, but doing it for semantic segmentation in a zero-shot manner. Okay, so the grouping mechanism in here is a lot of is quite also inspired by the old literatures in like semantic in segmentation, detection, and recognition. So essentially, in the old days, without deep networks, we have been working on like this kind of like graph models or bottom up, top down inference. You basically like pass the image into small regions and then bottom up to group them into larger regions and then top down to fine tune these regions. There are a lot of these kinds of layer models in the past before deep learning, but after like you have the fully convolutional network, everyone is doing segmentation in a more end-to-end manner. So in this work, essentially, I was thinking to try to bring a little bit back this kind of top-down group, bottom-up grouping into our deep learning model. So specifically, we are bringing the grouping mechanism into this kind of a vision transformer model. So given this image, it's like the other vision transformer. We have these image tokens to forward to this transformer layer. But a little bit difference is that we also have these learnable tokens, which you can see as some clustering centers. So it's just some parameters in there. And then we have this grouping block, which is essentially performing self-attention, not self-attention, but attention between the grouping centers and the image tokens. So in here is basically you can think of one step of clustering that you try to assign the image tokens into different center in here. And then after assigning this, you basically grouping the image token, small pieces of them into larger pieces of segments in here. And then we will forward these small segments to the next layer to basically perform more transformer operations and also grouping operation into become larger segments. So finally, these larger segments, we will basically compute average pooling in here to average the features from the larger segments. And then we perform a contrastive learning between this image level feature and the text features in here. So it's not directly actually performing contrastive learning between each region and the text. It's actually performing contrastive learning on the global feature for the whole image and the whole sentence feature, the two elephants in the jungle this morning. So in this way, the model can somehow still group the objects that is semantically meaningful to help this contrastive learning loss. So you can also correlate this a little bit to CAM, like Bolly give a talk before, I believe. So you can also relate to that. Basically, in CAM, you train a classification network, but then you can get the saliency map for each class regions. So this has a little bit similar flavor. Is that the VIT provides mechanism to group the regions together, and then the later is more like a CAM thing that basically use different region information mixed up together, have a global feature to do the contrastive learning, but then it can come back to each regions that represents a different semantic categories. So that is basically the framework of this grouping vision transformer to try to group the visual tokens into small segments and then larger segments, and then learn automatically for semantic segmentation. So are there any questions at this point? Yeah, so maybe are there any?
Yes, I think like we have this raise hand kind of thing. I'm not sure if you can see that. Yeah, so I have like some like maybe very technical thing, which is like the latent token.
Right.
Is that like a critical piece in here?
It's like
if
what?
you don't have this, I mean, like if you don't have this latent token, if you just do like self-attention between all the image patches,
right,
would it work? Or like maybe this latent learnable, group token is a very critical piece in this work.
Right. So I think the whole idea is reducing the small patches into larger segments, right? So you kind of need the mechanisms to, like, for example, the first layer of learnable tokens is actually 32. So after this grouping, you're reducing 196 visual tokens into 32 tokens to represent 32 small segments. And then later, you basically, the second layer we have is only 8 tokens. So you're reducing the smaller segments further to only becomes 8 tokens. So you basically need a way to merge this small, like this vision tokens into a smaller number of tokens. Yeah. So how do you merge them? Can you merge them by like, I don't know, average pooling or other things? But then somehow you need to merge them in a way that they formed a region, right? It's not just a regular grid separation, right? So we hope that it can be like more like more presenting to more variant shapes. Given different input, we have different segments as the output. So it's more like a transformer on top of the segmentations. Or you can think of first is superpixel and then larger segments instead of just a regular grid separation. So yeah, so I think the only way I can think of to do that now is to do this kind of assigning different patches into different clusters. Yeah.
Yep, I also have a question. The question is, don't you think, for example, that instead of late fusion like we did here for text and for visual information, we are just using it via contrastive loss, maybe we could like merge text information maybe in some transformer blocks, like maybe something in the middle, for example.
Right.
Maybe.
Yes. Yeah. Yeah, I think that's a great question. Great suggestion. At some point, we do think of like, for example, the learnable group tokens can be mixed with the text information. So it's more like it's more like a text-driven kind of grouping. It will be. Yeah, we didn't get to try that. I think we had talked about this at some point, but we didn't. Yeah, we have not get into that. But thank you for bringing it back. Yes, I think that would be interesting if you have this text information in the learnable tokens as well. So each layer is basically small text driven instead of right now it's more like I think in the beginning it's more like grouping in the low level without the text information. Yeah, it comes to very end. Yeah.
Okay, thanks.
I have two questions very quickly. So the first one is how do you generate the learnable group tokens? The second question is like now you use text encoder because you have the sentence to describe the scene. What if we change it to like tags of like class labels? Would that be equal to training a classification loss instead of contrastive loss?
Yes. Yeah, I think for the first question, so for the learnable group tokens, it's actually it's just a set of learnable parameters, and then it's shared across different instances. So you just maintain a set of learnable parameters and then use backpropagation to learn these parameters. You can think it of as like the positional encoding you use for vision transformer. It's just initialized with some weight, and then you use backprop to learn these parameters. And for the text encoding part, actually in practice we do besides the whole sentence, we do also try to extract each lambs out of this sentence, and then we input this lamb to the text encoder to extract the text embedding. But we find that if you just use one word, it somehow didn't work so well. So we need to put it in the phrase. It's like, because for example, we will construct a phrase like a picture of elephants and then a picture of jungles, something like that. So I put a picture of something up before the lamb and then put it into the text encoder, and then we somehow find that it's actually helping better to extract the features. Yeah, not sure why. And the text encoder is also trained from scratch as well. Yeah.
Gotcha. Thanks.
I had a good question. How much, like, what's the size of the image tokens, and how much does the sharpness of the semantic segmentation map depend on that? Yeah.
Right. Yeah. So this is still very coarse. So you will have the resolution is exactly the same as like the number of the image tokens. Like you have like maybe 16x16 resolution, right? So because you are separating the image into 16x16 tokens. So the resolution you can see is very coarse, and then the size of the learnable tokens is in the first layer is 32, and then the second layer is 8. So in the end, you have 8 segments. Maximum has eight segments. That's the current stage. Yeah, so the quality is still pretty coarse, but I can show some image later. Yeah.
Cool. Sounds good. And did we do some ablation studies about how much does the text encoder help in the semantic segmentation sharpness?
How much is the text encoder?
Yeah, so the text encoder, you use that as a contrastive loss. I was just wondering, if we remove that, then what's the quality of the semantic segmentation?
So the contrastive loss is used for training, right? So in the inference time, we just have each region, and then we basic computer similarity for each region's feature and the text feature there to do the segmentation. Yeah. Yeah, it's more like a query based, like you input a dictionary of text into the text encoder to get the features, and then each image region is finding its nearest neighbors. Yeah, among the text features.
Thanks.
Okay. Yeah, I can move a little bit forward. So essentially, we can see some grouping results like this, like some visualization of grouping like this. We just try to visualize the grouping, the parameters we learn. So we can have some groups that learns the eyes, some groups that learns the limbs. So essentially, the hands of the humans, and also somehow the legs of the animals. And then some groups that learns the background, like the grass. So just visualizing that the groups can automatically emerge to segment the regions like this. So we perform some testing on some standard data set. So essentially, we can do like zero-shot transfer to semantic segmentation to this kind of data set. First, perform grouping, and then do semantic segmentation without any further fine-tuning. It's just using this pure text image chain model to do the segmentation in here. As you can see, the quality is not so high for now, but then again, we didn't do any fine-tuning, and then you can use different labels to do the segmentations. It's not in a fixed vocabulary. Okay, so we also have this online demo. I want to show a little bit in here. This is in Hugging Face. You can also go to play with it. It's basically given an image input, you can get the groups in the bottom right, and then you can also input a text, and then you help you find texting, like labeling the regions. For example, I can label the regions in here with the robot, and then in here we have these images, and then segment it on the bottom right, and then we can find the baby girl in here, and then this is one of my students do it. So basically, you have this one piece image, and then you segment the human out, and then you input the Luffy, and it's able to find to segment the Luffy out. So I'm not sure though if actually the model has learned who is Luffy, but I think maybe it's like Luffy is close to human name, and then it's able to segment the humans out. So you can is labeling the human with Luffy. So maybe that is what happened. I'm not sure. But essentially, we show some show that this model can actually perform open vocabulary segmentation. So even just with image text training in here. So we show some comparison with clip as well. So you can use clip, first extract the image features, and then do some clustering, different ways to use clip, and then we basically adding grouping in between inside the VIT. It can actually help a lot in this case. Okay, so this is basically the part for the segmentation. So yeah, besides the segmentation, we are also very keen to do research in 3D scene understanding or 3D object understanding. So this is also important part for our robotics system. So essentially, in particular in this work, our goal is to, this is the, we call this work video autoencoder. So we try to learn the 3D structure and the camera trajectory from large scale videos instead of a fixed numbers of set of video. So the approach is really simple. We just train an autoencoder for the video. So input a few frames of the video of a static scene, and then you have this encoder which just disentangle the information into the 3D deep voxels and the camera trajectories. And then you basically entangle them back to basically use this camera to rotate the shared deep voxel across different frames. And then you rotate the voxels into different angles and directions. And then you correspondingly render the rotated voxel back into the input videos. So the input and output are exactly the same thing. So that's why we call it a video autoencoder. And we basically can I think the cool part in here is that we just only use the reconstruction loss to basically to learn both the 3D deep voxels and the cameras, and we didn't provide any ground truth supervision for the for training the camera. So essentially, both the structure and the camera are trained at the same time in a self-supervised manner, with only reconstruction loss, no depth, and no camera ground truth in here. So I find it that in that aspect is very interesting, because if you see a lot of work in real synthesis and other 3D work in NERF, all camera ground truths are always required, which really limits the number of videos they can train on. But in here, we try to just breaking through this and then try to make it work on more general videos without the constraint of the camera. So just go into a little bit of detail in here. So in here, we actually, in here, we didn't use any fancy rendering or volumetric rendering or any geometric rendering thing. We essentially in here, our 3D representation is actually quite simple. It's just also a deep features. So you can see it as a 4D tensor. So you have a reslet to extract feature and then reshape, and then you put some channels to the depth, and then you shape it to become a 3D features. So that's what we got in here. So there's no projection or reprojection or anything happening in here. And then you can compute the camera, and then the camera basically will do some 3D transformation. It's essentially just a fine transformation on the tensors you got, and then you do more 3D convolution, and they reshape back to the 2D features, and then you directly output RGB based on that. So there's no fancy any kinds of rendering technique in here. The only geometric transformation happening is basically in the 3D affine transformation in the beginning, in the middle. So that's basically the whole framework. Yes.
How do you get this camera pose here? Like, is it like also a learnable thing?
Yeah, yes, I skipped one slide actually. Let me just unskip. Yeah, so the camera pose in here is basically we also learn a separate legwork that you input 2 images. So every 2 images basically will output the rotation and translation in here to basically so it's directly learned by backpropagation. There's no supervision for here, and it's a relative camera pose basically. Specifically, we are basically comparing the computing the camera pose between the first frame and the other frames. So it's all relative to the first frame given the video as input.
I see.
It's like a visual odometry, right?
Yes, yes. But it's more like a shorter term. We actually train on 6 or 7 frames in here. So it's not like a very long term. Yeah. So in here, we show some applications. For example, the wheel synthesis. You can just extract features for the first frame, the deep voxel feature for the first frame, and then input the camera to generate the wheels behind. So it's trained on the real state 10K data set, and we can basically visualize like single wheel synthesis in here. But I think the cool thing is that because it's training on many videos, you can generalize to different kinds of scenes. For example, in the Minecraft, it has never seen. You can do some wheel synthesis in here. So even in this kind of Van Gogh painting, you can also zoom in this painting like this. So I think this kind of framework brings a kind of a better generalization properties, in the sense that if you just try to extract the explicit 3D representation for this painting, usually it might not work. Although in the end, we can see as we zoom in a lot, it's getting blur, and then a lot error accumulated. So our camera, the branch can also be evaluated. So essentially, we can also just perform camera estimation in here. So it's just comparing to structure from motion, and we can have a reasonable camera trajectory estimated. So here is a lot of examples. So that is basically about this video autoencoder. So the key point is that we can just learn both structure and camera at the same time without any supervision, and just use the reconstruction supervision. So are there any questions in here? More questions?
How do you decide the size of your 3D voxel structures? Or do you have any constraint here? Or?
Yeah. So in here we are basically doing it's not very, it's basically, I remember it's 32 cross 32 cross 32, like the height, width, and depth is 32 cross 32 cross 32, and then there are some channels. Yeah, so we tried larger ones, but then it's just much. We tried 64 or something. So I remember if you put the height and width into 64, at least at that time the training becomes harder, and then it seems somehow when you're doing the reconstruction, you try to render other views, it's more likely stay into the input source view. It doesn't work very well to render the other very different views. Keep it a little bit small, makes it easier to actually maybe I don't know, make it easier to rotate and generate new views somehow. That's something I remember. Yeah. So yeah, so basically in the middle is 32 cross 32 cross 32.
Yeah, maybe my question is more about, like, say you train this, and then if you do inference time, like is there any difference between like giving a very small, like a small bathroom image versus a very large conference room?
Oh,
for example,
I see.
Would there cause any issues because of
I
this
see.
side of the 3D voxel?
I see. Yeah, we haven't actually tried. So you mean that in different size of image, and then you get different size of 3D voxels, and then you rotate different size of them to generate different sizes. Yeah, I don't think we have tried that actually, but yeah, you can be interesting to try. I'm not sure, because I feel like in here it's not like semantic segmentation that you can input variants of image size. In here, the rotations is happening like in so I feel like the rotations really depending a lot on the size of the voxels. Like for example, if you rotate the voxels and then rotate it to 30 degrees, some part of the voxels will go out of the boundary, it will be ignored like that. Some part will not. So then so I think in this case, the learning might train to overfit to a particular size of the voxels. If you change the size of voxels during inference, yeah, I'm not sure whether it will still work because there will be other parts that is going out of the boundary after you rotate. So I'm not sure if that can be calibrated, like the parts going out of the boundary. So it's a little bit tricky there, I can imagine. Yeah, so I'm not sure. We didn't try that, but I would think it might not work. Okay. Okay. Hope that answer your question. And are there any thoughts?
So I was wondering, like, if this only works, like, what is the horizon that it will work? Like,
right.
I imagine after some time, like, error will accumulate.
Yeah. So I think it is just like, for example, this is more like 3-4 seconds of videos. So it's maximally we try 6 frames, something like that. I mean, the assumption is that the 3D structure, this deep voxel maintain the same across the frame. So it's not like when you're doing actually SLAM, you have these voxels build up, like the map build up across time. It's just the one thing. It's not accumulating over time. Yeah.
Got it. Thanks.
What's the frames per second for the 6 frame sequence?
Yeah, I think it's 20, 24, something like that. So no, but we do skip the sampling, like I think 2 frame represents 1 second, around that. Yeah, in our case. So we sample 6 frames, so it's around 3 seconds. Yeah.
I see. Thank you.
Okay. So I can maybe move on to the next. So I thought I did mention that, like, we didn't train any LERFs and implicit representations in here. We just use very simple techniques that you just reshape and then reshape back and then you do decoding, right? So, but during our experiments, we did try though, like try to train, like our voxels, and then we do volumetric rendering on the voxels, and then we try to render with NERF to get the image as the output. So it turns out to be very hard to to scale up the learning like that, and that optimization takes a lot of time, and then the training takes a lot of time. We didn't manage to make it work. So that makes me like to try to look into a little bit more on this kind of generalizing implicit functions and NERFs in here. So basically, we have this recent work that is try to kind of learn this more like shareable implicit neural representations or NERF. So we try to train a model that learns implicit functions from diverse images and videos and views of data, instead of just overfitting one NERF to one scene. So in this work, so we will basically handle both images and NERF, implicit representations for images and NERF. So as a very quick summary is that I want to talk a little bit about like there are different ways of like building implicit functions. So for example, the standard way, like for the most standard NERF, you basically can do just optimizing one implicit function for a particular instance or particular scene. So one MLP for one scene. So there are also like vector condition neural fields. That's why I call in here. So essentially, it's more like those SDF, deep SDF. Essentially, you're considering conditioning on a global latent code, and then you decode different latent codes. You can represent different shape. So one MLP is shared across different shape. But the way to do distinguish different shape is using different latent vector. So there's the vector condition neural fields, and then there's also a hybrid. So essentially, it's more like what we have seen. Like there's also some work that training implicit function and NERF on diverse scenes and diverse images. So essentially, you have an encoder to extract the feature for each locations, and then you use these local features to construct the feature map volume and then do rendering on top of that. But this kind of work also considered basically performing like learning the representations for local patches instead of have a very global implicit functions overall. So our idea in here is basically we try to learn the first type, like this more like a global type of implicit function, and across different instances. So in here, this work is more very close to this like there's also this meta learning of neural fields. So essentially, you learn an MLP, and then this MLP is more like an initialization, and then this can be used to fastly adapt to different images by a few iterations of fine-tuning optimization. So this is using Memo to do it. But instead of using this gradient-based meta-learning, so in our case, we basically try to do it in a more forward manner. So on the in the right figure on the left, you can see this is more like standard Memo. You have this initialization of theta 0, and then you just do multiple steps of gradient descent to get to the model you want. So in here, we're proposing a transformer meta learner in the sense that it's not doing gradient descent for multiple steps. You just use a transformer to replace or to simulate this kind of gradient step approach. Essentially, you give the weight as input into the transformer and the data input, and the transformer will going through multiple layers, and then the output is the updated weight for the current data input. So here is basically a more detailed picture. So it doesn't matter it's learning implicit neural representation for images or learning a LERF for multiple different views. Essentially, given this image input, we can make it into this visual token. And together with some learnable initialization tokens, we can go for a set transformer. And this transformer will output the weight, essentially the MLP weights for this implicit function. So you basically have this initialized MLP weights as input, and then you have this updated MLP weights as the output, and then you kind of reshape, reorganize this MLP weights into this MLP, and then use it as the implicit function for the input image. So it's more like a hyperlag work as well, but it's then so in here it's just we use a transformer to basically to generate the weight for this MLP. So we have some results in here, basically showing that we can reconstruct do reconstruct the image pretty well, better than the previous meta learning approach. And then you can also do some wheel synthesis approach, wheel synthesis using LERF. So essentially, given the input wheel, you can rotate it into different angles. So this is all doing with one forward pass instead of learning a LERF from scratch. You just can generating a LERF given this image input directly from the transformer. So are there any questions in here? Okay. So this is using camera. So by the way, so if you train LERF, so it's not generalizing that to use without camera. It's more like trying to train a global function, train a transformer that can generate the global functions for the input views or input image. Yeah, and in some way you can see that as like we are representing each image as the function, and then we are doing image to image reconstruction. Okay, so this is this one. So I think one thing I do want to quickly go through is basically some 3D representation work we learn. It's actually quite useful for some of the robotics tasks. So particularly, I want to mention this work that, so in this manipulation task, we actually use our video autoencoder to help to do this reinforcement learning for this manipulation task. So there are a lot of work that try to, like currently there are a lot of work that try to use MoCo and other self-supervised pre-training to basically to perform this kind of motor control. We just have a MAE, have a MoCo, and then plug into the RL to train. So in here, instead of continuously focusing on these large-scale 2D features, we are looking into actually learning this more like a 3D representations for this manipulation task. So instead of using a scene, we're basically focusing on this CO3D data set that you have multi-views of the objects. So we train our video autoencoder on top of this object-centric data set, and then try to apply it, basically applied to this robotics environment by acting ahead for reinforcement learning. So I will just quickly go through it in here. So essentially, we are still using video autoencoder, but just replacing a data set. And then in the simulation environment, we can also generate this sort of multi-view data that you can easily have different views of the robots when it is applying the task. So we first perform pre-training and then do joint training with reinforcement learning. So essentially, given one view, we can also get the features, the voxel feature, and then we can basically rotate it to different views to do the reconstruction. So we can actually fine-tune this video autoencoder in the simulation environment as well. And then we basically use these representations to train the reinforcement learning, to train the model-free reinforcement learning. So our manipulation task is just, it's still quite simple. There's some lifting, there's some pushing, and then there's also like this like packing box kind of task. But remember, all these tasks is performing by just taking these exact pixels as input. So it's all just based on the pixels input and directly output actions for the robot to do the manipulation. There's no detection or segmentation in here right now. So we compare to a little bit on previous representations, like people do MoCo and people do image-led pre-training. So during training time, we don't see much a difference, but then we find that as for transferring to the real world, from sim to real transfer, using 3D features helps a lot during this kind of model-free RL sim to real transfer. So I would also like to mention a little bit, like there are also like a current trend approach that trying to basically learn a LERF to basically learning this 3D representation from LERF and then use the representation to do motor control. So in that case, they can generate very beautiful wheel synthesis results as well as when doing the control. But I think in our case, we are basically trying to argue that it might not be necessary to have high synthesis quality for actually learning representation for control. It's maybe better to learn from large scale data with okay wheel synthesis results, but learn more generalizable representations so that can help us to do sim to real transfer as well. So that is some thoughts in here. And but in one single sentence is just like applying this video autoencoder representation to motor control. Are there any questions in here?
So like the core idea here is like through this video autoencoder, we can learn better feature and then can generalize better in inference.
Yeah. Use this as feature backbone extractor, and then you can train directly on simulation and then and directly deploy to the real world. So this is the real deployment, but we can see the simulation is actually looks like this. we train on this kind of environment, and then we directly deploy to this real robot environment. Yeah.
I see. And do you jointly train the representation learning with the RL, or you
Yes.
first train
Yes.
the video to encode and then fine tune?
We do the
training.
joint. Yeah, we first pre-train and then do the joint training. For both. So in here is training the RL and the video autoencoder reconstruction loss at the same time. Yes, but then you use pre-training from the CO3D dataset.
I see.
Okay. Yeah. So besides just training RL, I do want to also briefly mention some work we do in model-based control. So it's called TDMPC, Temporal Difference Learning for Model Predicted Control. So it's still mostly doing MPC. The key is how to basically learn the model, right? So I think so in here, I think the first contribution of TDMPC is not only learning the model, but also learning the value function. So essentially, you given this, like for MPC planning, we basically have a current state, and then we plan through some horizon. In here, maybe just 5 or 6 steps. So actually, it's 5 or 6 horizon. And then we plan locally. Given one state, we basically not only use the reward for this particular time, but also use a value function to estimate the future rewards that it can get after reaching this state. So essentially, we plan locally and then also combine a global or future value function to do the model predicted control in here. So this is one thing we learn. And another thing we do in TDMPC basically is, I think is particularly interesting, is that when we try to learn, a lot of people call the word model or the model for planning, is that we don't use image reconstruction to learn the model. Instead, we just use the reward to learn the model. So in during learning the model, the dynamics model, essentially we learn the representations when we are performing the temporal difference learning. We basically model-free RL to learn the representations. So you can see we use value and the reward to learn the Z. And then after you learning the Z, you can basically, based on this embedding, you learn the forward dynamics model. So the forward dynamics model is also based on this embeddings. You do this kind of future predictions. Given a state feature plus the actions, you predict next state feature. So it's operating on this embedding space. So in the model predict control, we were all performing planning in the embedding space. So instead of, so the key core idea in here is just how can we learn this embedding space, and then we basically try to use model-free RL and reward to learn this embedding instead of image reconstruction to do it. So I think this is quite different from a lot of model-based approach, and then I think it makes a lot of sense as from a vision people perspective, that like reconstructing everything in the world is really not necessary. So you might consider a lot of backgrounds and everything that's not really relevant to the dynamics happening here. So I think this is one way to search for other signals to learn the embedding instead of using reconstruction. So we show some results on like on this kind of very challenging environments on the like this dock environment running in this DeepMind control suite. I think it might be the hardest task there. So I think we are the first like approach that can solve it very well. And then the model-free approach and the previous model-based approach cannot really work on this task. So here are basically some curves. So comparing to humanoid and this dock environment. So using our TDMPC approach. Yeah, so this is just like one way to do model-based learning. So as comparing to the previous model-free approach, we can also use this approach to utilize our visual representation. So are there any questions for this one? Okay. So
yeah,
yeah,
I do have
okay.
questions.
Uh-huh.
What's the difference between this and the dreamer type of approach?
Yeah, so
and
for
I think
dreamer,
like DeepMind, they
right.
also have like this trying to learn this value rewards, also this transition model, right?
Right. So, but their transition model. So essentially, compared to Dreamer, the transition model, they're actually doing predicting the pixels. So essentially, the transition model requires the pixel supervision to learn the embedding, and then Dreamer is basically it's actually a model-based approach that you kind of learn the model and then use that model to basically train the reinforcement learning, right? So it's actually learning the model to, and then you use the model to construct kind of a simulator, and then you train your RL algorithms inside this model constructed simulator. So that is actually the approach. In here is actually quite different. It's like we also still do interactions. So the RL training is actually doing interactions with the actual simulator, not the dreaming simulator, right? And then we use that to provide supervision to train the embedding. And then the model is trained with these interactions without a construction. And in the dreamer is actually trained with the reconstruction. So I think although all the elements are there, like predicting values and then do forward dynamics is there, but it's actually quite different. In their case, it's actually training a word model, so you can do model-free RL on top. We're actually using model-free RL to help you to train the model, and then do model-based RL on top, like model-based planning on top. Yeah, I'm not sure if that, answers the question.
I see. I might have to read the paper in a little bit more details to understand the nuance. But I mean, just from the picture, for example, I think Dreamer and maybe also like some, I think there's also some paper from like David Saber, also similar to this kind of flavor.
But I think one thing that does distinguish a lot from this paper from other papers is that it does not really require the reconstruction loss to train the model. I think that is very different. If you look in Dreamer and all the other papers, they will still require reconstruction loss to provide constraint for the embedding space to learn the forward model, dynamics model. Yeah, I think that is the major difference. So yeah.
We have a question in our chat from Yuri. Yuri, maybe you can ask it directly.
Yeah, I can show it. Should the key takeaway for the task-specific supervision helps to shape the embedding space better? Yeah. So it does actually. This is a good question. So it does that, like we are learning the embedding for task-specific instead of embedding like a word model for everything. So it does kind of constrain, limited to the embedding to a particular task, makes the learning much faster than just learning a global embedding for everything. But to counter that, we do have also experiments currently, like training TDP MPC for multiple tasks at the same time, and then that also works pretty well. So in that sense, it's more like embedding that try to extract features for different tasks. But I think, as always, we are going to extract features for task related instead of just low-level pixel related or low-level cues related information. Yeah. Okay. Yeah. So I think that is for this work. I think I can go
like
quickly.
maybe I have like also
Yeah.
one more question, and then want to get your input. So you mentioned that maybe if the input is image, you don't want to do this reconstruction because you might
Right.
reconstruct some of the unrelated
Right.
pixel backgrounds,
Right.
right? Let's say, for
Right.
example, if the space is just a bounding box, for example, do you think it's better to also learn this model in the latent space, or do you think it's better to learn this model in the explicit, like because it's just a bounding box or positions, right? Like this abstract kind of domain. What do you?
Right.
I don't know if the
Yeah.
question is clear or not. Yeah, because I think like I saw a lot of model-based RL. They try to learn in this latent space. I think latent space might be very powerful, but also it might lack some of the interpretability, for example, because it's just some
Right.
high-dimensional vector space. But if the
Yeah.
state space is already in this very abstract level, do you think it's still
Yes.
beneficial to learn in the latent space, or it might be better to just learn in the explicit version, like just
Yeah.
basically doing some
Yeah. I get what you mean.
schedule
Yes.
prediction stuff? Yeah.
Yeah. I think that's true. So yeah, I'm always not like a big fan to just learning everything end to end. So I think this also provides us. I don't think I have the slide here, but I think this also provides the opportunity to basically. Okay, I do have the slides in here. So essentially, that maybe the latent space should not be just like just learning a latent representation for the pixels. It can be just using other vision models. So essentially, we can use the grouping VIT and the video autoencoder to actually maybe extracting some like semantically meaningful and also 3D representations from the images, and then do planning on top. So I think in that sense, it makes it more important to not using reconstruction as the objective. So in here, I think we do can have could replace the representation easily with all different things I have introduced before. If you just need a little bit report to do the fine tuning instead of reconstructing everything again. So I think in that sense, only using report as a supervision is quite convenient because we can just replace this small, actually a few convolutional legwork with this more advanced vision legwork, and then use the report to fine tune a little bit. Yeah. Especially there are also cases like multimodal. So in these examples, we have actually not only images but also state and as input, or different views of images as input. Yeah. Now, I'm not sure. Yeah, if that answers the question.
Okay, so it seems like you were saying like maybe injecting some more explicit
Yeah.
representation for the latent space is better than just a pure latent stuff.
Yeah. So it could portraying with, for example, portraying with this this group VIT, or like we explicitly have like regions extracted for extracted the different regions from the images, and then based on regions we do this planning. I think that will be. I think yeah, that is actually making more sense. But then we do need to fine tune a little bit to learn the dynamics in here, because it's not just it's just not just appearance of geometry. It's also there's a physical dynamics. So we do need to have some maybe some report and some other supervision to learn the dynamics in here. But definitely extracting more advanced vision features should help.
Okay, thanks.
Okay. So I think I'm not sure how much time I have actually. Do I still have time? Oh, I should end soon actually. Maybe I just quickly mention like some work I'm quite excited about. So we are also doing a lot of like imitation learning work in the lab. So essentially, we are we have a few projects on like learning with the dexterous multi-finger hand. So here basically just some results of grasping. We are doing more tasks now, but here are some videos showing that we can do some diverse like control grasping diverse objects and generalizing this kind of multi-finger hand manipulation to different objects instead of to the to parallel jaw gripper. So in here, especially we use some imitation learning technique. So how to get the demonstration data? We basically actually designed teleoperation system that only requires an iPad and a laptop. So it works like you have this human operating in the simulator, and then we actually can customize a robot hand in the simulator for the humans. So here is the calibration base, calibration stage. And we basically, given different human hands, we can actually have different size of humans. So you can feel comfortable with your own hand operating in the simulator. So you can basically just use this camera, and then you can play different manipulation tasks inside the simulator. For example, in here is opening the door. So in this way, you can collect a lot of different demonstrations on how the robot hand can operate in the objects in the simulator. I particularly like this system is that because we could potentially scale up data collection with mechanical turquoise as well. So essentially, anyone can just do this kind of operation in front of the camera, and then have these dynamic demonstrations inside the simulators collected. Once you have these demonstrations with this kind of customized hand, you can actually do some retargeting to different robot hands that actually can be used in the real world. So one demonstration collected on the top left, we can do some retargeting to generate demonstrations on the other three corners. So essentially, we can have Lego hands on the bottom left, which we actually use for the real world experiments. And for the imitation learning algorithm, we are basically using something that is combining a behavior cloning term with a reinforcement learning term, and then so this is just a DAPG algorithm, and then I want to show some basically results. So essentially, on the left is RL, and on the right is using imitation learning. We basically kind of show that using imitation learning, providing a more human-like grasp can actually give you more robust grasping. Whereas in simulator, the hand can find some way to hack the task. So this is flipping a cup. But in the real world, it's actually very hard to transfer if you just do it with RL because the physics doesn't match. But if you do it more like a human do, it's more easy to transfer with this multi-finger hand. So this is one work we do in here. And we recently, I was not very happy with the way to do sim to real based on images, especially for this kind of multi-finger hand that has complex geometries. So we are also doing some work that you basically train RL on top of point clouds. So you use point cloud input in real time, and then you train this RL policy using point cloud input to do model-free RL in here. So we find that especially for this more complex geometry context, physical context with complex geometry, point cloud seems to do very well for sim to real transfer. So here is our setup that you have simulation and the real, which is kind of aligned. And then we train a point cloud policy. I'm not going to go through much detail, but essentially we can grasp diverse objects with different geometries. And then this all can be transferred very well to the real world. So for example, in here, just some other videos showing the grasping results. But this time we are training the policy on top of the point cloud input instead of the image input in here. So this is grasping some bottles, and then we also have some current progress in opening the door as well. So try to actually construct the point clouds for everything in here, and then you can have more accurate geometry contacts to kind of try to do the open door task. It's not doing very well. It's just we're still working on it, but it's just show the potential that we can do a lot of different tasks. Like even this complex handle, we can still kind of play around it. We also make the door ourselves, so doing these experiments requires some skills in wood crafting as well. So this is basically some progress on the imitation learning side. So I'm very excited about these directions that you actually need a lot of like 3D understanding and a lot of contact reasoning to do this kind of task. And I think vision help a lot because you do need to learn from human. So how to pass human, how to do get 3D information from humans. This is something very important for this sort of task. So that's one directions we are putting a lot of energy on. So I want to go to the end, and we also have done some work on like this leg robot stuff that we kind of taking vision input from the camera in the front, and then we can let the dog. Yeah, it's also training model 3 RL and then walk around the campus. So this is also some vision-based RL work that make it work with this locomotion control in here. So I'm not going to wear a lot of details on this, but this is just a demo that's showing some obstacle avoidance. For like this is inside the campus, and I think I can show the you can avoid walking humans as well. So the training so the input for this one is basically the depth camera in the front, so you can see the left pictures are the input for the policy to learn this kind of model 3 RL. Yeah, so basically that's all. I think I can conclude from here. Hopefully it's not over time too much. So we are very interested in doing a lot of vision work continuously, and then this vision work will be very helpful for robot learning and then apply on other robotics tasks. I do like I think doing robot learning with real robot is very important. So most of our work now also have a lot of deployment and considering how to do sim to real and considering how to do learning in the real. So that's also the a strong focus of the lab. And then I think there are two, maybe in summary, there are two aspects that's important for vision for robotics. Is basically the input. So learning a better, more structured, rich representations is important for the policy input. But then on the other hand, for the supervision side, especially for our multi-finger hand manipulation task, so we see that if we can understand human object interaction better, and this information can basically provide supervision to provide better signals to perform robot learning as well. So I think vision plays very important roles in both the input and the supervision in these tasks. Yeah, so I think basically that's all. Are there any questions? Yeah.
Thank you, Professor Wang. Yeah, it's really interesting. I think it's also quite similar to what Nuro is doing. Basically, the self-driving is robotics, right? We need to do first like vision, I mean, but for us, like it's detection, 3D detection, segmentation stuff, and also like a lot of prediction and control. So a lot of robot learning. We also do RL stuff, and also like our end goal is also to deploy all this kind of system on loads in the real world setting. So there's also a lot of long tail case. Safety concern is a very big concern for us. So yeah, thanks for the work. Yes, very interesting, related.
Yeah, thank you.
I learned a lot.
Yeah. Thank you. Okay, there's a question actually. Do you learn your Q function for TDMPC in the learn space also? Yes. Actually the Q function, the Q function, the goal for learning the Q function is actually to supervise the latent space. So the latent space is shared among the model-free learning and the model-based learning. Yeah, the forward dynamics model also backprop to the latent space, and the Q function also backprop to the latent space. Yeah. Okay. Yeah. Okay. So if you have any more questions, just feel free to email me. Yeah. And I'm always welcome more discussions.
Thank you, Professor Wang.
Thank you.
Thank you for your nice talk.